Okay, it's a great pleasure to have Shao-Kai Jian as our speaker today. Shao-Kai got his PhD from Tsinghua University, and now he's a professor at Tuneng University. Over the years, Shao-Kai has done a lot of interesting works, ranging from topological materials to quantum criticality to quantum chaos and quantum dynamics. And today he's telling us about his new work on unconventional superconductivity. Shahai, please go ahead.
Good. Thank you very much for the introduction and for the invite. It's my pleasure to present this talk. So I'm going to talk about quantum Charge-4e superconductivity and deconfined pseudo criticality in the attractive SU4 Hubbard model. This work is a work in progress, so I will appreciate your comments and questions. Before we get started, let me acknowledge my collaborators, Zhou Quan Shiwei from Flatiron, Huan, who is my student from Tulian University, and Xuan from Tsinghua University. Okay, so here is the outline of my talk. I will first give a brief introduction to motivate the work. And then I will talk about the quantum phase diagram of the attractive SU4 Hubbard model. And then I will introduce the anomalous scaling behavior at the Charge-4e, Charge-2e transition. Then I will propose a theory to explain this anomalous scaling behavior, which is the SP4 gauge Higgs model and the associated pseudo criticality. Then I'll talk about the fate of physical electrons. Finally, I will conclude. So introduction. We all know very well about Charge-2e superconductivity, which is a condensate of two electrons. In this state, we have a flux quantization condition, and it often appears as a BCS instability of weak coupling Fermi surface. On the other hand, for Charge-4e superconductivity, it is a condensate of four electrons. And then the flux quantization of this state is half of the flux quantization of the conventional 2e state. This state is interesting because even in the mean field level, the Hamiltonian is interacting. If you write down the mean field Hamiltonian with this 4e condensate, this is already an interacting model. It is an example of non-BCS strongly correlated superconductivity state, and that is why we are interested in exploring this state. So Charge-4e superconductivity was proposed to be realized as a residue order of multiple component superconductivity at finite temperature. These include pair density wave, nematic superconductivity, and so on. So in this kind of scenario, in a zero temperature, the state is not Charge-4e superconductivity. It is, for instance, a nematic superconductivity, which breaks both rotational symmetry and the E1 symmetry. So you can imagine if you want to increase the temperature to restore the symmetry, there are different possibilities. So one possibility is that the rotational symmetry restore first and E1 symmetry restore secondly. And in this scenario, we are going to realize the Charge-4e superconductivity as a residue order at finite temperature. In recent years,
Sorry,
people
Shahai. Just
yes.
for general knowledge, vestigial order just means some finite temperature order that disappears at zero temperature.
Vestigial order means when you proliferate some topological defect and it will restore partial of the symmetry of the ground state. For example, here, this Charge-4e is a vestigial order of this ground state nematic superconductivity. And also this nematic is also a vestigial order.
I see, I see. Okay.
Okay,
Oh,
so
sorry. Can you
yes.
explain what is nematic superconductivity?
Oh yeah, you can just think of this as so to understand this, you can have a multi-component condensate, and each condensate carry different a quantum number basically. So we break both rotational symmetry and the U1 symmetry. Does that make sense?
I see. Thanks.
Okay. Yeah, and in recent years, people also propose Charge-4e superconductivity at zero temperature, for instance, in SU4 symmetric systems. And the intuition for SU4 symmetry is because when you consider n electron pairing, it can be naturally realized as a SUN singlet. So that is why people are concerned about SU4 symmetry here. However, the clear examples to host zero temperature Charge-4e superconductivity are still rare. And this motivates the question I want to address in this talk. So can a simple two-dimensional attractive SU4 Hubbard model host quantum Charge-4e superconductivity, and what is the nature of the transition into the 4e state? And the answer we provide is yes, the attractive SU4 Hubbard model hosts Charge-4e superconductivity through a deconfined transition from the 2e state.
Shao-Kai, do I need to have SU4 symmetry to realize Charge-4e superconductivity as
No, this is not essential.
But it's convenient.
SU4 symmetry is not essential. It is just you have a natural language to talk about the n electron pairing because this is a singlet state of
Okay.
SUN symmetry. So if you realize a state that doesn't break the SUN symmetry, right? At a zero temperature, that might be a like 4e state.
Thanks.
But this is not essential. Okay, so and let me move on to talk about the phase diagram of the model. So we basically consider a SU4 Hubbard model on a square lattice. So we have two terms, the nearest neighbor hopping T and the on-site Hubbard interaction. And this A is the flavor, so we have four flavor and the system is SU4 invariant. Here N is the local fermion occupation number. For this model at the generic fitting and at weak coupling, the Fermi surface will suffer a BCS instability. So if you consider a scattering event for electron from plus K and minus K to plus Q and minus Q, this is in the BCS channel, this process is marginally relevant for attractive interaction. So that means it will form a Charge-2e superconductivity. This is just basically the BCS superconductivity. This is for the weak coupling. On the other hand, if we look at strong coupling limit, so we just have two terms. If the interaction is much bigger than the hopping, the second term dominates. So let's look at the second term. So this is the, as I said, this is the Fermi occupation number at each site. So it can take value from 0 to 4, right? So if you can write out the energy for these five states, and what you can realize is that the low energy sector is given by the vacuum state and the fourth electron state. Just from the simple counting, you can already see this. Then if you want to perturb the state from this large degenerate ground state, you add this hopping term. You can do the perturbation order by order in a strong coupling limit. So the lowest order is this second order process. So we consider a vacuum and a electron quartet, meaning 4 electrons occupied in this site. So you can have electron hop to the left and then hop back. So this is a second order perturbation, and this will lead to a nearest neighbor coupling. However, if you want to realize a hopping of 4 electrons, you will need fourth order perturbation theory, because each time you move 1 electron, so you need 4 hopping term to realize such a movement of this electron quartet. So this will realize the hopping of the quartet. There's another same order coupling, which is the nearest neighbor next to the nearest neighbor coupling. So the process is here. So we have 4 electrons in the middle. It hop to the left, or maybe hop to the right, and then hop to the left, and hop back, right? And this will realize this NNN coupling next to the nearest neighbor coupling. So in a strong coupling limit, this realize an effective Bose-Hubbard model of the quartic. So we just truncate the Hamiltonian to the lowest energy state, and this can be written in terms of a bosonic operator to create this electron quartet or annihilate the electron quartet. So we have the hopping, which is in the fourth order. We have also the NNN coupling, also in the fourth order. So this is the effective model at a strong coupling. And this already tells us something because, yes.
Oh yeah, please go ahead. Please go ahead.
Okay, so this already tells us something because now the natural language to describe the system becomes electron quartet, right?
I have a random question. So now
Yes.
at each site, there are four flavors of complex fermions. Then in principle, by designing the Hamiltonian, I can have an SO8 symmetry
Why is it SOA?
because there are 8 flavors of Majorana fermions. This is also why for spin 1/2 electrons, sometimes we can have SO4 symmetry. My question is basically, is there anything interesting if I think of for so for the spin 1/2 case, analogy is that we can have single occupied sites. They form as what we usually mean by the spin. We can also have the no occupied site and the doubly occupied site. They can form the pseudo spin. This pseudo spin, if I design some spin Hamiltonian in terms of the pseudo spin, usually the magnetic order in this effective spin Hamiltonian means superconductivity in the electrons. I just
Yes.
wonder why the similar story also happens here.
Yeah, you're actually catching the next slide.
Uh-huh.
Yeah, you can write this as also as a spin model. This is just spin 1/2 if you like in the lowest if you truncate to these two states. So one is spin down, the other is spin up. But of course, you can write this in terms of the Bose-Hubbard model. These are hardcore boson. And in this language, okay, we have the strong coupling, and we present two terms in the same order: the hopping term and the NNN coupling term. So there will be competition between these two terms. So if this hopping term dominates, we get this superfluid state in the Bose-Hubbard model, and this corresponds to the Charge-4e state in the electron language. And I think this is precisely what you talk about for the spin Hamiltonian. If we have an order if we have like SY order in the plane, then this is a Charge-4e state in this language. Of course, if the coupling, NNN coupling dominate, then possibly we have charge density wave state. And fortunately, this a similar model, I would say, has been studied in this paper. They consider 1/4 fitting of the Bose-Hubbard model. And this is their phase diagram. So we can see both superfluid state and this solid state is basically charge density state, if you like. But we clearly see a big portion of superfluid state in the model. So then we can put out the conjecture of the phase diagram of the SU4 Hubbard model. So in a weak coupling, we have a normal Charge-2e superconductivity, and in a strong coupling, possibly we realize this spin fluid state, which is Charge-4e state in the electron language. And we want to see if this is correct, right? And so we implement a determinant quantum Monte Carlo calculation. We know the attractive Hubbard model is sign problem-free at any fitting. However, it has a so-called infinite variance problem. This is This is problem of a long tail distribution of observable in the Monte Carlo samples. So if you look at the observable, the 2e correlation, for example, and this is the probability density. This is a log-log plot. You clearly see this long tail. And this long tail will lead to the variance of this observable being infinity. And 4e is even worse. So the exponent for 4e is actually worse than the exponent of 2e. And that is why people haven't looked into this model closely. But fortunately, this problem has been solved by Zhou Quan and Shi Wei recently using so-called exact bridge link method. You can see here for illustration. So for the 4e correlation length or correlation function, without the method, you can see this huge error bar, but with this exact bridge method, you can bring the error bar to be very small. And then let me present the phase diagram using determinant quantum Monte Carlo. The observable we choose is just 2e and 4e correlations. So 2e are just pairing of 2 electrons and 4e for 4 electrons. So we present the zero temperature phase diagram at 1/8 filling. And here, this is the Charge-4e correlation ratio. And you can see from the figure, we simulate for different system sizes, and they cross at some point for different sizes. For small u, it increased. That means we have a finite 2e condensate. For large u, it decreased. That means we don't have the 2e condensate. So there must be a 2e transition. On the other hand, if we look at the 4e correlation function, there's no crossing first. And then if you look at different system sizes, you increase the system size, they basically saturate to a same value. They collapse onto each other and saturate to a finite value. And that means the 4e condensates remain finite across the transition. So in the 2e phase, Charge-4e condensate is kind of free because Charge-4e is just a square of 2e. So this is a secondary order, if you like, in the 2e phase. However, when the 2e condensate vanishes, the 4e becomes the primary order. So we clearly see a transition from the 2e to 4e superconductivity in the model happening around 0.89 here.
Sorry. At 1/8 filling, how many electrons are there in the unit cell?
So it's a 0.5 electron in one site.
Then, in the previous discussion, if the attractive U is large, then at each site, I want to either have 0 electron or 4 electrons.
Yeah.
Within that
So,
harmonic, if the chemical
Good.
potential is set to be 0, then I should have 2 electrons per unit cell, right?
Yeah, good. So here, I perform the strong coupling analysis for the harmonic itself in a canonical ensemble. And also in the simulation, we fix the number of electrons. We don't touch the chemical potential term here. So this is a canonical ensemble. We fix the fitting for the simulation.
Then, if I perform the strong coupling analysis for the canonical ensemble, then it basically means I will have many sites. I will have many more sites with no electron than sites
That's right.
with more
Yes,
electrons.
that is what happened actually for the strong coupling limit.
I see.
For this 1/4 fitting, I don't have the figure here, but basically this solid just means some site will have 4 electrons and some sites are just empty.
I see. Thanks.
And you can imagine if you lower the fitting to 1/8, it is harder for this solid state to be stabilized.
Thanks.
Sure. Okay, so we established this phase diagram. Basically, we have the transition between 2e and 4e by tuning the coupling. And the next question we want to address is what is the transition behavior? So we would like to figure out the symmetry breaking pattern for the transition. So now we have a pairing of SU4 fundamental. So the electron is a SU4 fundamental, and then we have a pairing of two electrons. That means we have pairing of two SU4 fundamental. And according to the group theory, it decomposes into these two irrep, and basically the superconductivity is this anti-symmetric irrep. But we can still have some residue symmetry left. So you can consider, for example, the transformation of the 2e order. So delta is the 2e order, then the transformation is U and U transpose acting on both sides. So the residue symmetry is if there exists a subgroup of SU4, say we take an element of the subgroup of the SU4, then the element will leave the order invariant, and that is what we mean by residue symmetry. So to classify the residue symmetry, there is a mathematical statement that any complex anti-symmetric 4x4 matrix can be brought to a screw Takagi normal form. So that means we can always bring this 4x4 matrix into this form where we have two parameters, lambda1 and lambda2. So they are characterized by these two numbers. So if they are equal, then the residue symmetry is sp4. If they are not, the residue symmetry is sp2 cross sp2. And
Sorry.
this has been discussed in this paper. Sorry, go ahead.
Can you explain what is sp4 group?
Yeah, sure. I will explain this in the next slides.
Okay.
But basically, if you take lambda1 to be lambda2, so if these two are the same, the sp4 group is defined by this relationship.
Okay.
Meaning that you take an element from the sp4 group, it will leave this equality invariant. Okay, so to really pin down the scenario for the residue symmetry, we instead consider density order. So now it's a tensor product of anti-fundamental and fundamental, and we have this irrep, non-trivial irrep here for the traceless part. This singularity is just the trace. And also for this irrep, if we lower the symmetry to sp4, fortunately, they are still non-trivial representation. So we have 10-dimensional additional representation and a 5-dimensional vector representation. So we can look at the behavior of the density order to see if this sp4 symmetry is broken, right? If the density develops some order, then of course it transforms non-trivially under sp4, then sp4 is broken. If it doesn't develop any order, then we can say sp4 is invariant. For example, if sp4 is broken to this sp2 cross sp2, which is isometric to SO4, and this is exactly this five-dimensional vector. So if the 5-dimensional vector develop an order, right, then it will break the sp4 down to sp2 cross sp2. It is just like a 6-dimensional, so 5-dimensional sphere, and you pick one direction. So we examine the density order, and here is the density order in terms of different system sizes and the interaction strength. We don't see any crossing, and more importantly, we see it scales down all the way to 0. Actually, when you extrapolate the system size to infinity. So that means density order doesn't show any ordering. So the residue symmetry we believe is the sp4.
So if the 10-dimensional adjoint representation develops some order, what's the remaining symmetry?
Good point. I'm not sure.
Mm-hmm.
But here we can rule it out because both of them are non-trivial representation, and we don't see any feature of the.
Mm-hmm.
So yes, and then we can say the spontaneous symmetry breaking pattern is from SU4 to sp4. And SP4 is, of course, a subgroup of SU4. Then we can think of writing down a Landau-Ginzburg-Wilson theory for the transition. And before that, let me talk about electrons. So we actually also calculate the gap of electron from the imaginary time propagator. So it behaves as an exponential function, and we can extrapolate or extract the gap from this exponential behavior. And this is the result. So we can see the single particle gap is always finite across the transition. I mean, it's finite everywhere here. So it is now natural to formulate a pure bosonic Landau-Ginzburg-Wilson theory based on symmetry. So this is not a symmetry forbidden phase transition. This is totally consistent with the principle. So we can use the coset theory, construct the linear sigma model. So a standard process is just you pick up a symmetry breaking state. So this is like a reference state here. I use this omega to denote this matrix. This is like the, you pick just one reference state and you use the broken symmetry generator to parameterize the fluctuating field. So the fluctuating field will bring the relevant reference state to explore the Goldstone manifold. So here we have the reference in the middle, and then we use the broken symmetry generator to explore the Goldstone manifold, and then we can write down the linear sigma model, which is shown here.
Shao-Kai,
Yes.
I have some kind of complaint.
Okay.
So you see, you are at like 1/8 fitting. There's some kind of fitting anomaly which is not reflected in this nonlinear sigma model. How do you deal with it?
I'm not sure about this 1/8 fitting anomaly about.
In any case, if so physically, we know that due to the Lipschitz-Martis theorem, if the fitting is 1/8, if the system preserves the symmetry and is gapped, then it has to develop some topological order. Meaning, if I change the Hamiltonian without changing the fitting, then if the system is gapped and preserves the symmetry, then it develops some topological order. But from this nonlinear sigma model, it appears that in the strong coupling limit of the nonlinear sigma model is a trivially disordered state.
Okay. Yeah, that's important message for me. And maybe this is the reason the Landau-Ginzburg-Wilson theory breaks down at the transition point. I would like to talk more about this later with you,
Sure.
perhaps. Thanks. Right, and then let's stick with this simple Landau theory and look how it failed to describe the transition. Okay, so we can utilize the isometry between this SU4/SP4 and SO6/SO5 to write down a simpler. I mean, it's the same theory basically, but in a simpler language. This is the SO6 linear sigma model. And people have studied this model previously using 4 minus epsilon 6 loop RG study, as well as Monte Carlo study for classical O6 model in 3 dimensions. And actually, the result for these two studies match very well between themselves. So you can see the exponent match between themselves, but the enormous dimension do not match with our results. So we have this determinant quantum Monte Carlo result. The enormous dimension is given by 0.85. But from the Landau theory, it is given by 0.03. So it's very inconsistent with what we observe. So as I said, so from the principle, Landau theory is not forbidden. But the prediction of the Landau theory is inconsistent with what we observe. And let me move on to propose a theory to describe the discrepancy between these two. And this is the SP4 gauge Higgs model and the pseudo criticality. So we need a different critical theory to describe two things. A, spontaneous symmetry breaking from SU4 to SP4. B, large order parameter enormous dimension around 0.85. A natural construction is from fractionalization. This is because in this framework, the physical order becomes a composite operator of fractionalized degrees of freedom, and it may naturally acquire a large scaling dimension. So a convenient or straightforward construction is to consider a matrix field Z. So it's a matrix field containing two indices, and we make one of the index to be SU4 global fundamental, and the other index we promote it to be SP4 gauge anti-fundamental. And the reason is that if this field condenses to a diagonal matrix, this SU4 index is logged to SP4 index. And we know SP4 is a gauge symmetry, so it never be broken. That means that we have realized the spontaneous symmetry breaking for the global symmetry from SU4 to SP4. And the other one is obvious. Any physical order must be a composite field of at least two Z field, and it will have a large scaling dimension. So with this idea, right, we have the this matrix field. It has both SU4 global symmetry and SP4 local symmetry. We can write down gauge invariant quantities from this fractional degrees of freedom. So we look at the table. This is just the representation of the field under different symmetry. So we have the global U1 symmetry. We assign a charge 1 for Z field. And as I said, it's a global fundamental and a gauge anti-fundamental. We construct a gauge singlet. This is the order parameter. So this is just the composite operator to describe the 2e condensate. We have two Z's, so it is charge 2, and then it transforms as a global anti-symmetric irrep. And this will realize the transition from the global spontaneous symmetry breaking from SU4 to SP4. We can also write down the Charge-4e operator, which is just the determinant of the matrix field. It has global charge 4, and it is both singlet for global SU4 and gauge SP4. And finally, we look at the thermal operator as well, because this can be the tuning operator for the transition, and this is a singlet for all the symmetries. So once we have this field, we can consider this field being condensed or being gapped. So when we have this field being condensed, we realize the Higgs phase. It condenses, if it is condensed as a diagonal matrix, our identity matrix, then of course the order parameter is non-zero. And it realizes the spontaneous symmetry breaking. On the other hand, if Z is gapped, then in the low energies, this SP4 gauge boson will confine.
So
But still, when it is
just
yes.
to make sure, in the Higgs phase, the Charge-4e order parameter is also non-zero.
Yes, that's right.
So it's a Charge-4e superconductor with a remaining SP4 symmetry.
Yes, it's a Charge-2e superconductor because 4e is just you can get 4e for free, right? Because you already have 2e.
Oh, then what is the? Oh, I see.
So this 4e is present across the transition. You have 4e finite in the 2e phase as well as in the 4e phase.
Thanks.
Right, and then for the confined phase, Z is gapped, and then the gauge boson will confine. Okay, then we are allowed to write down the critical theory using this fractionalized degrees of freedom. We promote this global symmetry to have NF flavor. So we have SUNF matters. That means this A index is promoted as the SUNF global fundamental. And according to the symmetry, we can write down the critical theory. So here we have the critical theory for this Higgs field Z. And due to this gauge symmetry, it is minimal coupled to a non-abelian gauge boson, denoted by A here, where this T is the SP4 generators. And for non-abelian gauge theory, the Maxwell term will contain self-interaction between gauge bosons. And for the second line, this is the symmetry allow for boson potential. We have three different potentials here. This is the theory we are looking at. And the tuning parameter is R. So the proposal is that when R is less than 0, we're going to have the Higgs phase. It is the Charge-4e phase. On the other hand, if R is positive, we have this Higgs field gapped, and then the gauge field will confine. So at I equals 0, we propose this is a deconfined transition in the language of the non-abelian gauge model.
Sorry, just to make sure, when the Z is
Yes.
gapped, why is it a Charge-4e superconductor?
Very good. So here I actually omit one more term. So in the original theory, when NF is equal to 4, you are allowed to add a determinant here.
Oh,
So there is a potential given by the determinant. But after we generalize the theory to NF be larger than 4, then this determinant, you can also write a generation for the determinant for SUN matters. But the point is that that is higher than the quartic term, so we omit that in the critical theory. But basically, across the transition, this determinant is finite and is allowed in the theory.
I see. But can I also think of this Z as instead of thinking of Z as a generic matrix, can I think of Z as being generated from identity matrix by either a left multiplication of SU4 or a right multiplication of SP4? In that case, I guess the determinant of Z is always fixed to be 1.
But a general Z is, I think Z is more general than what do you describe? Z is a
It can
general
be,
matrix. Yes.
yeah, it can be more general, but can I somehow, when I do the pattern construction, can I somehow use this kind of the other type of Z? This is like using rotor instead of using canonical boson.
Mhm.
Basically, I'm asking whether there's any analog of rotor for this Z.
I'm not sure about that.
Yeah, thanks.
Sorry,
So, yeah.
I have a quick question. So here,
Go
how
ahead.
do you see the SP4 residue symmetry in the charge 4e phase?
How do I see that?
Yeah, from this critical
So
theory.
actually, the Charge-4e is SU4 symmetric.
Oh, I see.
So the thing is, this 4e, in terms of the global symmetry, of course, it's SU4, and this 2e is SP4.
Yeah, then I mean this SP4 gauges. So in the charge 2e phase,
Mhm.
you should not have that gauge symmetry. I mean the gauge symmetry is Higgs, right? So
Yeah, it's
so
already Higgs.
and how do I see there is a SP4 symmetry, global symmetry there?
Yeah, so basically the point is that when this is Higgs, Z is not gauge invariant. So you must construct a gauge invariant thing, operator. And here, the order parameter is constructed by this one. This one is gauge invariant. It carried this representation, and as I said, it breaks the symmetry from U4 to SP4.
Okay.
It is actually from this delta, this canonical delta, because here this if you like, this SU4 index is logged to this SP4 index.
Oh, I see.
So the residue symmetry is SP4.
Okay, thanks. I see.
Yeah, and this is our proposal for the deconfined critical point between the Higgs phase and the confined phase. And to verify that, we carry out the one loop RG for the theory. So we have a few couplings. We have the gauge coupling. We have also the coupling for the four bosons, the U1, U2, and V. And then we can carry out the one loop calculation based on this Feynman diagram. And I just represent the RG equation for large enough n, right? Large NF. But remember, the RG is controlled by epsilon. So this is a 4 minus epsilon calculation. It is not controlled by n. We can group the coupling into a vector for simplicity. So this W is the coupling strength. And we solve the beta equation. And we find a stable IR fixed point. And this is given here from this equation. So you can see the gauge coupling G for the first component is non-zero. And the second non-zero coupling is U2, is this coupling. And both U1 and V are 0 for this stable fixed point. And it is easy to, this is stable fixed point, and this is easy to see because you can look at this. So the this U2 here, right? It generates a negative sign. Of course, the U2 here also generates a negative sign. That makes U1 and V irrelevant. Basically, they flow to 0.
So why do you use epsilon as the control parameter instead of 1 over NF?
Yeah, very good. I'll talk about this in one slide. Yeah, and we claim this is a deconfined quantum critical point, and of course, provided the monopole event irrelevant at large enough n.
So in this context, what is the monopole?
Yeah, this is a good question. This because SP4 is a compact group, I would expect the existence of monopole, but I haven't really looked at this monopole event.
So whether there is monopole is determined by the fundamental group of the gauge group, pi1
Yes.
of SP4.
It's
Is it? What is it?
I think it's some integer. I don't, maybe integer. I'm not sure about this. Okay, let me move on. And of course, in general, the monopole event is irrelevant. It has large scaling dimension if NF is big. Right, and then what do we find? So here is why we need 4 minus epsilon calculation, because we want to control the calculation and we try to vary n or vary NF. And this is what we find. The calculation is controlled by epsilon, but we can treat NF as a continuous variable. And then we find a stable fixed point will collide with an unstable fixed point at the critical NF star. And then they move to the complex plane. And we call it this collision point, the collision fixed point. To see this collision between fixed point, we can project the RG equation along the collision direction because they will move toward each other and there is a direction they really collide. And you project the coupling into that direction and also project the RG equation into that direction. And this makes the story very clear. Now, this S is the coupling along that direction. And the RG equation is simple here. So this delta is given by the difference of NF and the NF star. So you can see if NF is greater than the NF star, delta is positive, and then we can get two real solutions. And these two correspond to these two real solutions, these two real fixed points. However, if NF is less than NF star, delta is negative, and the solution becomes a complex. It is a complex pair, a conjugate pair in the complex plane. And this leads to the pseudo criticality. So if we fix delta to be less than 0, solve this function, you get two fixed points in the imaginary axis. And it is away from the real axis by square root of delta. So the real RG is flowing in the real axis. The RG is flowing in the real axis. But provided delta to be small, it will be controlled by the fixed point here for a long time. And people also call this a walking scenario for the complex CFT. So we can calculate the long RG time if delta is small. We can calculate that it is given by 1 over square root of delta. So if delta is small, we have a long RG time. Translate this to the model, it means between L max and L min, it is controlled basically by the fixed points here. And this leads to the pseudo-critical behavior where, of course, there's no real critical exponent because it is drifting. But what I'm saying is that between these two system sizes, it is basically controlled by the collision fixed point up to a small number. Of course, provided this delta is small. Then we can go ahead and calculate this fixed point exponent. So the drifting exponent is given by this collision fixed point exponent, and we carry out the one loop calculation, so we can get this one. And we look at gauge invariant composite operators, including order parameter, which is a Charge-4e condensate here, and the thermal operator. So these two scaling dimensions relate to the enormous dimension and this nu here. And here is our result. You can see even from one loop calculation, our result is pretty much agree with the numerical result in TQMC. Of course, nu is within the error bar.
I'm
But
sorry,
we can do,
excuse me.
yeah.
I have a question. So
Yeah.
if NF star is not an integer, then what's the physical meaning of it? And what's the physical meaning of calculating the exponent at the collision fixed point?
Yeah, very good. Right, NF in general is not an integer. The point is that we calculate the exponent at NF star because we believe it controls the vicinity around it by a very long RG time. And we believe that NF star is near 4. And our calculation actually consistent with our belief.
I see. Thanks.
Okay, let me move on, and we can actually do more, right? We can extract critical exponent depending on the system size. So here, the correlation ratio if it satisfies the scaling law, it will behave as this universal function. And we can use some ways to extrapolate or to extract the critical exponent at different system size. So provided, for example, two system size L and L plus 8, we can calculate the exponent here. And we plot the exponent as function of L. And you can see for small system size, it suffers from finite size effect. Then for large system size, it try to decrease. And that is consistent with the drifting to a first order transition, because eventually the RG flows away and ends at the first order transition. We can also calculate the or extract the critical exponent for the order parameter, because we have this relation at the criticality. So you can see it also exhibit a systematic drifting as we increase the system size. It drifts towards 0, which is also an indication of first order transition. But our theory are consistent with the drifting. You can see this blue dashed line coming from our calculation. Okay, and I move to the last part, the fate of physical electrons. So the question we haven't really answered is, how does this SP4 gauge Higgs theory emerge from an electron model? So we consider electron fractionalization, and this is very similar to the story of symmetry mass generation. So an electron can be fractionalized into a matrix and another fermion. So in terms of this fractionalization, we have actually a U4 gauge redundancy, because you can multiply U4 matrix in between them. And I can list the symmetry representation of each fields. We know this Z field already, but now it carries the anti-fundamental of gauge U4 group instead of SP4 group. And F is a neutral fermion, and it doesn't carry the global SU4 either. So it's just a gauge U4 fundamental for this F fermion. And you can we can look at the Charge-4e phase. So Charge-4e phase is also a Higgs phase in terms of this U4 gauge group. So consider this Z condensed. Then the U4 gauge symmetry is completely Higgs. And what is going on is that this F parton is identified as the physical electron, because you can see here from the fractionalization, C is now proportional to F modular a quasi-particle weight rho, which is the condensate of Z here. And as we know, the electron form 2e superconductivity, that means the parton also form a superconductivity in the 2e phase. This is kind of boring, but if we look outside the Higgs phase, we don't have a direct identification between the physical electron and the F parton. So we expect the F parton to form a Fermi surface. And this Fermi surface will couple to gauge field, the SU4, sorry, the U4 gauge field, which is the U1 cross SU4. So we have both abelian and non-abelian gauge boson coupling to the Fermi surface. And the result for the correction from the Fermi surface to the gauge boson is to make the tempo component massive. So this is the screening of boson from the Fermi surface. However, the transversal component of both gauge boson remain gapless. So we have this couple theory, and we still have the gapless transverse component for the gauge boson. And next question is, what is the effect for the F parton from this gapless gauge boson?
Shao-Kai, just to make sure, I think I missed it. Why did you have to consider the U4 gauge field instead of the SP4 gauge field?
Yeah, because I want to relate this to the to the electron. I want to see how the calculation, because in the Monte Carlo calculation, we always probe electron. And I want to see how this SP4 gauge Higgs theory emerged from the electron theory.
But after doing this pattern, I think one can first condense something to break the U4 gauge group to SP4.
Yeah, very good. Yeah, that's the idea. I want to make the condensation natural enough. So here it's the maximal redundancy. I would say algebraic redundancy if you just try to write C in terms of Z times F. Of course, you can try to Higgs this U4 gauge group by some other field. But let me just try to make it natural. You will see how this is obtained, how the SP4 is obtained.
Yeah, but in terms of the pairing stability, if you keep U4, then the U1 gauge field wants to suppress pairing. And
yeah, very good.
SU4 wants
Yes.
to enhance pairing. That's the competition.
That's right. Yes, that is what I am going to say here. Right. So the Fermi surface, right? Because it coupled to the Gablitz boson, the Gablitz boson will renormalize the pairing channel. And as you said, of course, the abelian gauge boson suppresses the pairing, but the non-abelian gauge boson enhance the pairing. So here, this is from the diagram. So we have electron with opposite momentum, and they can exchange gauge boson. And this leads to the correction in the BCS channel. For abelian gauge boson, because this vertex is its identity, and if you project this to the BCS channel, it gives you a positive sign. That means a suppression in the BCS channel. On the other hand, if it is a non-abelian gauge boson, then the vertex is non-trivial. You get a gauge generator, the generator of the gauge group. And when you do the projection, there's a negative sign here, so it enhances the pairing. So there's going to be a competition between these two effects. We have a positive suppression and we have a negative enhancement. So our proposal is that the gauge coupling, non-abelian gauge coupling, is greater than the abelian gauge coupling, and this leads to the pairing of F parton. And the effect of the F parton is A gaps out the parton itself, B Higgs the U4 gauge theory down to SP4, and this make the SP4 natural enough to emerge from the electrons.
So Shao-Kai, here, suppose you really start with the U4 gauge group, then
Yes.
one has to also study the RG flow of E squared and G squared to determine at the fixed point which was larger.
Very good. Yes, we calculate that, but I haven't added here. From our calculation, what is interesting is the ratio of these two coupling is marginal.
Yeah, this is actually a result I obtained 6 years ago.
Okay.
I had a
Good
paper
to know.
on this in 2020. I have 2 papers on this.
I see. So you published that paper?
Yeah, in 2020.
I see. I will look into that. Yes. So the ratio between them is marginal.
Yeah, that's actually something that has been worrying me for the past 6 years. The ratio is marginal in the leading order calculation.
Yeah,
But
in the leading order calculation, that's right.
But in principle, at high orders, the fixed line may collapse into a few fixed points.
Yeah, of course. So here it's just a proposal, and of course the physics can also go beyond the perturbative regime, right? So if I start with a very big G, I think it's going to dominate the physics.
But we also want the calculation to be controlled. So G is not that big. So I guess at this point, at least I don't have any controlled way to make the conclusion for the past 6 years.
Okay, I see. Right, and yeah, I think that's pretty much all of it. I'll conclude here. So I present the result of the Charge-4e superconductivity in the attractive SU4 Hubbard model. And I propose a deconfined transition to that phase from a 2e phase. And we can also look at different directions in the future. For example, the SU4 model is sign problem free, and we can look at different deformations and different lattices. We can look at the non-perturbative effects like the monopole and the topological effect. And finally, as you already mentioned, we are also looking at the non-Fermi-liquid coupled to both RBD and non-RBD gauge boson. And maybe we can talk about the result. With that, thank you very much for your listening. Happy to take questions.
Yeah, Shao-Kai, thank you very much for the interesting talk. Are there further questions?
Sorry, and I have a question related to the one before. So is it possible that we can see topological order in this effective theory?
No, for the current model.
Then do we need to have topological order around the critical point?
Oh, at a critical point is deconfined. If you would you like to talk this as regard this as a topological order, it is gapless deconfined fixed point.
Thanks.
I guess maybe the question is within this pattern construction, within the field theory, how do we get to a topological order?
Yeah,
Currently,
that's
no, we
what I
don't have the topological order.
Yeah, but maybe by gapping out the F fermions, say putting them into some train bands with certain train numbers, that will generate
Yeah.
some topological order.
So there's actually a related talk, related work recently about the topological Charge-4e superconductivity, where they have this SU4 level 4 theory. It's Chen-Simon's theory.
Okay, other questions?
So in your previous presentation of the numerics, I wonder if you can see the SP4 symmetry from the results.
Right. This is not direct probe of SP4 symmetry. No, I think it's direct probe of SP4 symmetry because you probe this density order and you see it doesn't order, right? So if SP4 is somehow broken, it will allow this to be non-zero. And if something is allowed to be non-zero, it is naturally non-zero, right?
But I think so that means that you cannot compute something and see the symmetry via the transformation of the indices. It's not a direct observation of symmetry. Is that?
Yeah, if you can construct a more complicated correlation to see exactly the SP4 symmetry.
So I mean that's in principle doable.
In principle, you can do that.
I see.
Right.
Yeah, thanks.
Hi, I have a question. I may have missed this, but is there any experimental signature that distinguishes the Charge-4e phase and the Charge-2e phase?
Experiments, you can look at flux quantization, right? So the flux quantization condition for these two superconductors is very different.
So could you elaborate more? I'm not really familiar.
Yeah, so this try to insert flux, right?
Yes.
And it will be quantized at some value. You can try to probe this value.
Oh, okay, I see. Thank you.
And did you say there's some experimental motivation for Charge-4e?
I think there's always experimental motivation for Charge-4e, right? This is a new state.
No, I'm asking, is there any signature of some material that shows Charge-4e?
Yeah, I remember there's a paper by Jian Wang from Peking University, and his group report. I don't I don't remember this very clearly, but definitely he has a paper about this. It's
Ah,
in Kakomi metal material, I think.
I see. Mm. Okay, any other questions?
Oh, by the way, I just checked the fundamental group of SP4. So here you mean SP4 means complex SP4 or real SP4?
Real
USP4.
XP.
No,
Real.
you mean USP4, that the double cover
Yeah,
of
US.
SO5.
If it's USP4, then it's really compact and connected, so it should be like trivial fundamental group.
So we don't have the monopole event here.
Yeah, very good.
Okay, that's good. Thanks.
Any other questions? Okay, if not, Shao-Kai, thank you again for the very interesting talk.
Yeah,
We
thank you
can
for the
log out.
question and the comments.
Yeah, we can log out. Bye.
See you.